Hello students, in this video we will have 7th illustration of chapter 5. We have several questions given here. First one is magnetic field lines show the direction at every point along which a small magnetized needle aligns. Do the magnetic field lines also represent lines of force on moving charged particle at every point? Before going to next, we will discuss the first one. Now here we are talking about two quantities. Do the magnetic field lines also represent line of force? Now magnetic field and magnetic lines of force, what does it mean? So in case of electrostatics, we have F is equal to QE, and what is the direction of force? Direction of force is direction of electric field. So electric field line and electric line of force, both are same thing. But when we talk about magnetic force, the formula is QV cross B. It means that the magnetic force is perpendicular to B as well as B. What is B? Magnetic field. So when we say magnetic lines of force, this F we are talking about, which is not in the same direction as that of B. In fact, it is perpendicular to it. So answer to question A is no. The two are not same. Second one, magnetic field lines can be entirely confined within the core of a toroid but not within straight solenoid. Why? Okay, let us understand what is a solenoid and what is the nature of its magnetic field. So we know that if this is solenoid, when we allow current to pass through it, the magnetic field lines come out from the solenoid like this, and the solenoid actually behaves as if it is bar magnet. Okay, so field lines come out, and some field lines they actually bend and they form closed loop. So this is the nature of magnetic field of solenoid. What happens in case of toroid? Toroid is a case where we bend solenoid, and then what we get is this shape. So field lines they actually form closed loop. So the question here is, magnetic field lines can be entirely confined within the core of toroid, because in toroid we don't have two ends, so magnetic field lines do form closed loop as shown here. Okay, whereas in case of solenoid we have two ends, one end and the other end. So from one of the ends magnetic field lines come out, and in other end magnetic field lines enter. Third one, C. If magnetic monopoles exist, how would the Gauss's law of magnetism be modified? So here I would like to recall Gauss's law for electric flux. If you remember the formula, the expression was closed integration E dot dA is equal to sigma q by epsilon 0. So if I have single charge, I can say that electric flux linked with the closed surface is q by epsilon 0, right? Now in case of magnetism, we have similar law for magnetic flux given as B dot dA is equal to 0. Now why it is so? The reason is that whenever we consider any closed surface, and if I consider some magnet, say this is the magnet, and I say that the north pole is inside the closed surface, but yet what I am talking about is not only outward field or outward flux, the field lines are also entering. Okay, so whichever number of field lines are going out from the surface, same number of field lines are entering, and hence what is the net flux? The net flux is 0. But what if single north or isolated south pole were in existence? In that case, the condition would have been slightly different. In that case, we could imagine isolated north pole, say this is north pole, and then we can always say that there are magnetic field lines coming out from north pole. Okay, and now if I'm asked what is the magnetic flux link, the answer is not 0, okay, because field lines are going out but not coming back. And in that case, the expression would have been B dot dA. Now look at the analogy. If you have E dot dA is equal to Q by epsilon 0, instead of charge, we have pole strength. So I'll have pole strength M, and wherever you have epsilon 0 in denominator in electrostatics, we have mu 0 in numerator. So this would have been the form of Gauss's law for electric flux if magnetic monopoles were in existence. But luckily or unluckily, we don't have a single isolated north pole or south pole, and hence uh, this form is not reality. Okay, this is the form which we use because whichever number of field lines come out from north pole, same number of field lines enter from south pole. Moving to next, does a bar magnet exert torque on itself due to its own field? Answer is no. Because in bar magnet all the domains are aligned and there is no resultant force, so there is no question of torque, or there are no forces acting along different lines, so there is no question of torque acting. Does one element of a current carrying wire exert force on another element of same wire? Now, answer to this is yes. If you have one wire carrying current, magnetic field or magnetic force of that wire can definitely affect any nearby wire or charge passing by. But the wire cannot exert force on itself. Lastly, magnetic field arises due to charges in motion. Can a system have magnetic moments even though its net charge is zero? Now, answer here is uh, first part, magnetic field arises due to motion of charges. Very true. Can a system have magnetic moment even though charge is zero? What does it mean? Its meaning is, suppose if I have an atom, we know that in atom we have electron moving. So if I consider single orbit and one electron moving, I can say that there is a magnetic dipole moment. So for electron moving like this, we can say that there is some magnetic field or magnetic dipole moment. Now, what if I have 5 such electronic orbit? Then corresponding to each one, I have dipole moment, and this 5 may be negating each other, may not be negating each other. So it is very much possible that the resultant dipole moment of atom is not zero. What about charge of atom? We know that in any atom we have equal number of electrons and protons. So net charge of atom is zero, but not necessary that net dipole moment is also zero. Okay, so answer here is that it is possible that the system is having net charge zero, but yet non-zero dipole moment. That is all for illustration 5.7. Thank you.